Hello, hi. My name is Neil Fang from Cysic. Sorry for the delay. So in this talk, I'll show like from computation graphs to like production level ZKEVM nodes. Like we did like basically rewrite a lot of things like in the ZKVM tech stack. So the talk will be like 3 parts. The first is like we compare the difference between this like HAL, which stands for hardware abstraction layer approach versus our graph-based approach. Then the second is like we like our ZKVM we named as like variance, and right now is the version number is 0.1.6. We do some implementation of it on the different hardware such as like GPUs and also FPGAs. And then the third part is like how this like ZKEVM node should work. It should be like 1, 2, 3 instead of 1, 1, 1. Okay, yeah. So let's first talk about like what is like HAL approach and then graph approach. So HAL approach that we wrap around like each kernels like using like this like APIs, and whenever you want to call this kernel, you just call the API and it will do the job for you. So it's like this like approach supports running the same proving structure like in different hardware platforms. And the graph one is like sort of different. It encodes the whole process, whole proving process as a graph, and then you do some like translation, you do some like coding regarding to this like graph. And we can say like right now like the AI community usually adopt the second part since it's like more fit to the like the GPU like architecture. But the ZK community like since like we start from Hello 2 or Gnark, which is like pure like CPU execution, and we usually just say like if you recall there is some like Z-price competition before where like people optimize the MSN, which stands for multi-scalar multiplication, and then like NTT, like we optimize like using GPU or FPGA to optimize this like kernel, since like in the whole process, these kernels takes a lot of time. But yeah, so that's like why like the normal like ZK community, like they start from the HAL, since they benchmark the process and thought like some part is like more time consuming, so they want to optimize that part using some specialized hardware such as GPU and FPGA. So here is like a normal or like previous or like several ZKVM, like how the coding paradigm is like. So you first you do some wraparound on the internal core options, such as like allocate your buffer or some other things, and then you build your like some kernels, such as like a commitment kernel or like the entity kernels based on this like internal cores. Then there will be like the third step will be like a proof function which like glue over all these like kernels together. So that's like a normal like typical ZKVM implementation paradigm is like. If we want to use a picture to illustrate the process, is like we have the CPU, which will first run this like build command. Then it will like call the GPU to do a lot of things, like such as like doing the commitment, to evaluate the polynomial, evaluate the constraints. There will be some like communication between the CPUs and the GPUs, since like probably like you will use like the CPU to do the Fiat-Shamir hashing and all the other things. So it's like this like straight line, like each hardware will do their like corresponding job, and then they talk to each other. So that's the HAL mode. And of course, like we can saw some disadvantages in this process. It's like since there are like many kernels which will happen on the CPU, on the GPU side, so it's very hard to optimize the kernels from this global perspective. And these like kernels, they need to synchronize with each other, which also takes some time. And like more things like if you want to like start the kernel, start some chip on GPU, it also takes some time. So which means like it's difficult to achieve some global optimization. And second, second is like we treat since the HAL will treat the things like as a black box, and there are some interactions such as like the Fourier-Shamir transformation and the ILP reduction, which remain like hidden from the proving process. And the third one is like it's hard to translate or like rewrite the code like to some other platform. Since like if you want to rewrite it to like FPGA, then it takes really some time to do so. So that's some like disadvantages in the HAL approach. And yeah, then let's move on to say like how the graph mode is like. So to warm this up, you need to implement the ZKVM. We have like 3 approaches. Like first is like direct implementation, which like you just directly implement the ZK proving function in Rust, in Python, or in some other languages such as like the Glark or like the Hello 2, the original Hello 2, I mean. And the second, like there is some embedded like DSL into this like direct implementation. Yeah, so that's the second layer. So it's like from shallow to deep. And the third one is like you design some like DSL, such as like Carol or Noah, like to encode the like how the function should work. But you need to compile it like into some other things to make it work. Yeah, so the HAL approach basically encodes the computation to be proved, but the graph mode will encode the whole proving process, which is like more comprehensive. Yeah, so here is like we use a picture to illustrate the graph mode, which like the CPU will first compile this like whole proving process into a graph, into like a DAG. It's a pure data structure. And then like we run all these things on the GPUs. Like will be like continuous like GPU execution, no CPU like round trips. So like the GPU doesn't need to talk to the CPU and other things, which means like we can achieve this like a globalized optimization across like all kernels to make it like faster. And the kernels, they don't need to like synchronize with each other like too frequently. So like in our design, we have like 3 parts. The first is a circuit representation, which is like mainly used by the end user. We'll try to make it easier for the end user to use it. And the second is ILP reduction. So ILP reduction care about the correctness or the soundness of your ZKVM. And then there is a high performance computation, which like we just want to achieve like as fast as possible for this kernel. Yeah, so previously I would say like the PO or Circon, PO or PO2, like then they separate the circuit representation from the ILP reduction and like high performance computation. But in our approach, like we separate like all 3 things. Like so like each part will just care about their like jobs, like don't need to like interact too much with other. Yeah. So here is a result. Like so our thing is built on Cisc. The latest version of this, guys, I remember it's like 0.16. We implement so the comparison right now is like done on like 1590 GPU card, and we achieve. I mean like last week is like 6%, but right now we are improving. It's like almost like 10% for now, and the code is also on ZKVA on its proof. Yeah, but like we are switching from I guess like from rest to guess, so like we are still catching up with the block. So so the screenshot I take is like a days ago, and we are catching up with the latest block. After that, we can do the proving. Yeah, so here is the results compared with Cisc. And as I just mentioned, like the encoding of the whole ZK, the encoding of the whole proving process will allow us like to translate the pure data structure into other hardware platforms as well. So we also do it on FPGAs. The FPGA like right now is a very preliminary result with just like HAL's like friendless synthesized C++ code. Yeah, we didn't do any optimization on it yet, and it's showing almost the same performance per watt as GPU. So like for For the metrics, for the hardware, there are like two metrics. The first is performance per dollar, which means like how much you pay for your hardware. The second is performance per watt, which means like what's the energy efficiency of the thing. And I believe by optimizing the FPGA or not, then we can get probably like a slightly better performance in terms of like performance per watt compared against the GPU. So right now the FPGA just run around 100 megahertz, and normally it runs like around 300 megahertz. So still something like we can do. And yeah, since like Cysic, we started a hardware company, like we do a lot of hardware acceleration. And one of the goals for Cysic is to design some specialized ASIC chips for ZK. But yeah, we are just not very sure if the market is big enough to digest the chip. But we still believe that if we ignore the upfront cost, the ASIC will still be the be the ideal hardware to run it. Since on ASIC, like we can basically decompose the module like into like many smaller ones, and this like inter-module communication will be treated as like first class on-chip flow, which will make things like much efficient than doing it on FPGA or like GPU. Yeah, so there are like so many like things like we can customize if the market is big enough and we think like big enough to pay the upfront cost for chip tape out. Yeah, so here is our summary on the hardware. Like I believe like 3 years ago we write a blog post to say what's our take on GPU versus FPGA versus ASICs. We still think it's almost the same as before, but right now the ZK algorithms, they converge or not. So when we wrote the blog like 3 years ago, like there are so many ZK algorithms in the space, but right now they converge or not. Like the GPU still remains the production performance path. Like if you like, it's still the main proving power for ZK workload. And the FPGA is still, we use it as a prototype for the ASICs. It represents some like architecture design, but it's not the endpoint. And one more non-technical thing about the FPGA is like it's not very easy to acquire the FPGA chips. So which means like, yeah, you also need to pay a lot, like compare against the GPU. And we use FPGA learnings like as a quantitative guidance to the ASIC design. If there's still like demand in the market to come up with ASIC, then like we are very happy to do so. Yeah, so this is like how the ZK EVM node should like, and it's supposed to be a demo, but I don't have time to show it up. So it's so like I guess like the audience right now is like very familiar with ZK EVM nodes, which like instead of re-execute the blocks, you just need to have some like provers to generate proofs for the block. Then you just verify the block instead of like re-executing the block. Yeah, but there's like still some questions like we need to think about. The first one is like what the provers will fit in the general like Ethereum roles. Will it be like some separate role, or like it will be probably like the relayer should be the one to do the proof, since the relayer can see the blocks and it will just choose probably like the most the blocks has the most guess to do the proving. And then we need to design some like incentivizing rules to mobilize, to motivate the provers to generate the proof. If it's just the provers and to do the proof for each block and what they are going to get from the block, since they are like without the proof, the gas per block is limited, but with a prover, the gas limit can be like hugely increased. And so what's like the cuts the provers should take like from like boosting the gas limit. Yeah, so that's something like I guess the Ethereum Foundation should think about. Yeah, so if you are interested in, like, here is our code repository. We open source the code several days ago, and we also write like 3 posts, like the explaining the details of the graph modes and like our take on different hardware, plus like what will be the ZK EVM economics will be like in the Trinergy posts. Yeah. Okay. Thank you.
Thank you, Leo. We don't really have time for questions, but maybe people can join you in the outside the auditorium. Thank you, guys.